So myself, Ravi, and my colleague Sumanth, we will be talking about how do we manage Flink operations at GoJek and how do we work around that. So a little bit background about GoJek. So GoJek is one app for all your needs, and most of our operations are mainly in Indonesia, but then we are expanding to other Southeast Asian countries as well, including Vietnam, Thailand, and other countries. So GoJek started in 2010 as a phone-based like a ride-hailing service, but in last few years we have now grown into having like more than 18 products revolving around payments from ride-hailing and even from the food delivery and everything. So we have a wide range of products like ranging from all these different areas. So the agenda of the talk is going to be that how do we manage operations around Flink, specifically around like how do we do resource provisioning, what are the challenges we faced in the starting, and how like what was our approach to solve those particular things, and the similar for resource isolation, and we'll talk about data quality. How do we make sure that like whatever data that goes to the Flink is like the data quality around that is we are making sure that it's of right quality. We'll talk about how we manage and monitor our clusters in general, the Flink clusters we are running. And in case there are cluster failovers requirement, even for the Kafka cluster, which is like mainly our input stream, or the Flink cluster itself, then how do we deal with the cluster failovers? And then the final, we will also talk about a little bit about like how do we do chaos testing on those Flink clusters, and how do we do load testing as well.
Can you guys hear me? Hello? Yeah. So, as the data engineering team here, we are looking for patterns of how data can move within the organization. So, being a company with so many different businesses, it's naturally evolved into a lot of microservices, which don't naturally tend out to be an event-based way of things. So we try to enforce, go to the teams, talk to them and see how they can leverage Kafka and event-based asynchronous way of transacting within the organization. And we build a lot of applications, frameworks, so that any team which wants to leverage this kind of pattern do not have to code themselves. So they can just use our applications and just manage a few configurations and have it deployed and get their use case solved. That's the main motto of our team. So talking about scale, we have a huge scale in it. This is just the Indonesian market, all these numbers. So the location pings are huge. Like we have a huge base of drivers. We get close to 2 billion location pings from these drivers every day. And the booking events that we receive is in the order of 25 million. When I say booking events, whenever somebody creates a booking and whenever some booking is allotted a driver or a booking cancels, so all these are booking events and we receive about 25 million. And also we leverage Kafka and Flink for getting an understanding of how our services are performing. So all our API services have their stats published to Kafka, like how long did every single API take, what was their response code, how many of them errored out. So all of these events themselves go upwards of 3 billion. And this is just to give an idea of some of the use cases of Flink within GoJek. So search pricing, what is the demand in a particular area? Like how many bookings are coming in versus how many drivers are currently showing available in that area. So we need to be able to process this information in real time so that we can tell drivers which area they need to move towards so that they get better rides, and so to match the demand and supply. And API health monitoring was something that I just spoke about. So if somebody writes a new service, they will be able to see how well their APIs are performing, how many of them, what percentage of them errored out, all using Flink aggregations. And driver allocation, again, so what is the acceptance rate of driver in an area, and what is the order conversion? And again, it's similar to search. And of course, fraud detection, if somebody is logging in too many times, how many times did they receive a 401, like unauthorized? Is somebody trying to hack into the system? So we are able to act real time on all these situations.
So most of these things actually, like if we talk about like the entire process of how we go from having like from scratch just where the cloud is sitting and then to making sure that all these use cases are filled. So the very first thing we talk about is that resource provisioning. So what happens in our case is that since like GoJek has so many range of products, more than 18 products, and each team work on their own fashion. They have their like own set of team and then building on their own services in a microservice fashion. And then there is international expansion also happening at the same time. So what happens with us is that we get load of requests in terms of as soon as international expansion is happening, we have to create the set up the entire infrastructure for that particular region as well. And then even within the teams, if the new use cases are arising, and then we are making sure that okay, there are like proper resources are provisioned for that particular use case. So all these resource responsibilities fall into the data engineering team. Some of the challenges we face around that is that one is that since like these different teams have different products, and they have their like some of those products have their own regulation, for example payment system. So we have to be on multiple cloud providers including like Google, AWS, and then in certain cases we also have to make sure that we run on our own data centers as well. So any provisioning we do, we sometimes have to do it to the multiple clouds and as well as to our own data center hosted. And because of these same reason, international expansion or other teams coming, or because of the load testing, we have very frequent number of clusters getting created. These clusters that we are talking about, like even the Flink clusters, which we run on the Yarn or on the Kubernetes, also the Kafka cluster, which are the ingestion system to the entire system. Then another challenge is that all this process, since it's like so many requests coming, it's not like a one-time thing happening in like a month or so. So then it becomes very man-hour intensive, and the whole process is very repetitive. And this, at the end of that, it also becomes very error-prone in terms of, because there are like so many configurations you need to manage. You need to launch a new cluster with how many brokers you will launch to launch, how many nodes, worker nodes you want to have. So many configuration happening. It becomes a little bit error-prone as well. So the way we have dealt with this particular challenge is, this is how like our entire provisioning systems looks like. So we have a service, we call it Odin. So Odin takes care of anyone who wants to create a new infrastructure. So it makes sure of managing that particular thing. And then on other side, we have Flink module setup and the Kafka module setups. These modules are built with Terraform plus Chef. So Chef take care of like the all, we use Chef for like all the configuration management and everything. And then we utilize Chef inside the Terraform custom written modules to make sure that the entire, even the infrastructure provisioning is happening as well as the configuration management is happening. And in terms of, so it's like data engineering as a team, we provide the entire pipeline to all the teams so that they can create even their own cluster. We need to do it just supervise that. So we also make sure of that authorization happens in terms of who from within those teams are like able to create those particular clusters. Once all that is done, then we have one system we call Tesseract, and the Tesseract is more or less like it's an infrastructure as code. So any change or any cluster that someone is creating, the whole thing is written as infrastructure as code in one particular project. So anyone from any team wants to create a cluster, they have to raise a pull request, and then that comes to us. Then we have another system is like, because like so many multiple clouds we are running, and then there are so many VPCs inside that as well. So there are really good chances that whatever clusters you are creating within the subnets, there is a really good chance of address network clashes as well, right? So we have a custom return service which we call Ghana. So Ghana makes sure that like if you provision one particular cluster in a subnet with certain IP address range, then it makes sure that is registered, and and it makes sure of allocating new resources whenever the new request for a new cluster comes in. So Ghana in a way makes sure that there are no network clashes happening, no address clashes happening in the way. Then the whole thing goes through the pipeline, and then the entire infrastructure is getting created on the cloud, any of the references run. And then we store the state on the remote backend as well, so just to make sure that anyone can make sure that, okay, what is the current state of the entire infrastructure. So this is the example of like if someone wants to create an Flink cluster entirely, which makes sure of the entire configuration management, launching up your like virtual machines or creating a yarn cluster even on the Google Cloud. So all they need to do is just include this particular module, specify their master configuration or worker configuration, and it makes sure that that particular cluster is launched. So from a user point of view, that's all they need to do. In terms of how, like, making sure this entire system, like, what was the impact of is that our provisioning time kind of reduced to 90%. And now we were also able to, like, on the fly create infrastructure even for the load testing. We on the fly create it, and when the load testing is done, then we just tear it down. Like having the entire resource provisioning of all the clusters as infrastructure as code made sure that like we have better visibility, and it also made sure that the whole system is self-serve. Like each team on their own can provision their own clusters, Flink clusters or the Kafka clusters. And we as a data engineering team doesn't have to kind of interfere into that whole process.
Here we talk about how we manage all these resources there are multiple teams which use all these resources unknowingly at times. Like somebody might use a join job on a very heavy topic, and they'll be consuming a lot of resource. So we need to make sure that one team gets its own dedicated set of resources, and if somebody makes a mistake, let's say somebody cancels a job and it's only their job, like it doesn't they don't end up canceling somebody else's job. So this is one of the wrappers that we have around managing a Flink. So we have this for all the applications we have around Kafka and even Flink. So why is like we have a growth team, for example, who suddenly decide that, okay, I'm going to incentivize all those customers who have not been active for the past 1 month, and they just write a script which is not throttled and just pump data into Kafka. So if we had just one Kafka cluster, the other topics on that cluster would suffer. Maybe they have some transactional topics. So this is an undesirable outcome. And what if a non-critical job ends up taking more resources and forces the yarn cluster out of resources for something which is critical? And if we have just one huge Kafka cluster, let's say there is a lot of under-replicated partitions, or some partition goes offline and there's some problem in disk, then the entire organization would suffer a huge downtime. And it's also, if somebody makes an error and you have a organization-wide downtime. So for these, we have dedicated clusters and dedicated clusters of Kafka, dedicated yarn clusters, and these are all managed by teams. There are people who are authorized to act on them, and only they can edit the jobs in their clusters. So here's a diagram of, so these are our various Kafkas here, and various yarn clusters for the jobs. And each of these is managed and authorized for only certain teams. Yeah, and we have our own application called Atlantis, which manages the deployment of the Flink jobs and also governs the access. So the way we have decided to differentiate between Kafka is through the criticality of topics. We have transactional topics like booking topics, and we have some topics which are very heavy in terms of throughput, like the driver location pings, but it's okay to skip a few events. So these are configured differently with different retention, and yeah. So with these we have classified the Kafka clusters as, for example, the location stream is the Kafka, which is where we are okay to lose events, and it is purely for the high throughput. And then we have the conch stream and log stream. So these handle the API logs, which we were talking about, basically how much time each API is taking, and what was the status. So these are pretty heavy streams, and the main stream is one which has the critical booking logs. And yeah, so Flink clusters also are managed in a similar way. This is a UI of our portal. So this is an admin view, so we are able to see all the different Kafka clusters. And so there are user groups, Kafka clusters, and Dagger is our name for Flink jobs, so that's the yarn cluster. So these are sample yarn clusters that we can see. So we have some just for testing purpose, and we can all spin them easily with the Terraform module that we have. This is a preview of a Flink job creation or edit page. So this is how it looks for any of our users. They have to first start with a schema. So every topic is associated with a certain protobuf schema. So they have to select what is the class of that schema. And once they have selected that, the portal shows them the options of what are the compatible Kafka topics that they can source data from. And once they've done that, they just write a SQL. So we don't offer our users Flink as an application where they can code. So it's purely configuration and SQL. This has enabled us to reach out to a lot of teams, and even people who are not developers are able to get their hands and try to see some real-time data and understand patterns and come up with solutions. Okay, this is about data quality. So how do we ensure that in a organization which has 15 plus teams and which cater to different businesses as well, how do we manage that there is compatibility between data which goes around? Let's say a team A produces a certain kind of event which would be consumed organization-wide by different teams for different purposes. So to ensure consistency and less room for errors, we had to think of some measures. So these are the things that prompted us to take those measures. One is JSON is weakly typed. JSON is the regular API contract that we have in most of our microservices. But for events, we wanted something which is more strongly typed. And also, we wanted something where if somebody made a mistake, even if it's strongly typed, like we have protobufs, right? So people can make breaking changes. Even if they made errors, we should be able to work with it somehow. And what if somebody knowingly made an incompatible change in schema of the event, but deployed it in a bad sequence? Like you can have breaking changes, but you need to take care of the order in which that breaking change gets deployed across services, and what if that was not handled? And another thing when working with real-time data is the applications which consume your aggregated data should account for data not being available at the right time. For example, we have search pricing where we want to know what is the demand and supply right now in these areas so that we can better incentivize drivers to move across regions. So let's think about supply. So supply is the number of drivers who are available for rides in a given area. And if this data is not present in the system, it is not equivalent to 0 drivers being available in the area. So when you do an aggregation, it's very easy to misunderstand this situation as, oh, there are 0 drivers available here, so I need to send more drivers here to fulfill the rides, so I'm going to search the prices. But in reality, what would have happened is the data itself hasn't arrived. So the applications which work on top of real-time aggregations also look for certain number of data points. Only if it finds X number of data points, only then will it act on its logic. Otherwise, it'll fall back to a default behavior. Yeah. Yeah. So these are something which I discussed. So protobuf is what we use because it's strongly typed, and it makes people conscious of what changes they're making. Even if they move a field, there is an index. So they are allowed to rename the fields as long as they maintain the same index in the protobuf. And we also maintain different versions of protobuf. How we do that is protobuf, there is a descriptor for every message of a protobuf, and the descriptor itself can be serialized into a byte array through a descriptor.proto. So a team is free to create their own protos, and there is a pipeline which will convert them into small files, which are then downloaded by all our applications at runtime for any particular schema, which are version controlled. And they're able to get the descriptor, and the descriptor has the information required to serialize or deserialize the messages. Yeah, so the pipeline version creates a version file of all these descriptors. And what this allows us to do is, if somebody has made a breaking change in the schema, then we can rerun the job with a previous version. And this is very helpful if you realize something is wrong on the hindsight, then you can still go back and switch to a different version of the protobuf schema and again rerun things. And the last point is the one which I already discussed. So where there needs to be a distinction between no data versus the aggregation resulting in zero. So for example, surge pricing calculation only happens if there are enough points available in the system. For whatever reason, let's say the job is lagging or the job went down and there are no data points, then the surge pricing will not be calculated and it will just do a default behavior. So one of the important caveats that we provide for the users of our platform is monitoring. So irrespective of what products we offer, it has to come out with a way to monitor, and so that teams can set up their own PagerDuty or alerting on top of it. This is our typical stack. So we have Telegraph agents on all boxes, and so StatsD is what we used organization-wide. And the data goes into Influx. From there, it's either picked up by a Grafana dashboard, or we also have capacitor scripts, a capacitor server and tick scripts, which will trigger through a Git project. Grafana is something where we can visually see where the metrics are, and you can see the threshold, and it's very easy to manipulate. So Grafana is the popular one. And from there, we have PagerDuty, Slack, Datadog. So these are just some of the sample dashboards that we have. So as you can see, they're templatized for a particular cluster and a particular job, and you get all these statistics. The advantage of using a templatized dashboard is that you just set up one dashboard, and that dashboard will give you an ability to provide dynamic links, wherein you can give the name of the templates in the query params, and it'll show you the stats for that particular combination. So here, for example, if I provide a URL with Aziz Dagger and that particular cluster, it is going to show up this. So all we have to do is, for a user in our portal, we just have to create a link with those variables, and when they click on it, they'll have the view, which is just for them and the job of their interest. So we make use of the Flink StatsD jar, which pushes all this data. This is a dashboard which we use for monitoring how are the resources across the clusters, but they're all based out of the same StatsD metrics.
As we mentioned in the starting, so another very important aspect for us is that what happens if the input stream, which is the Kafka for us in terms of all the data aggregation, what if one of the Kafka cluster goes down completely? Or what if the Flink cluster, which is actually running a job, Yarn cluster, which is actually running a job, completely goes down? And we have more than, given 7 to 8 stream we run, we have more than 20, 25 clusters running in the same ecosystem. And then you can just think about having it for multi-countries as well. So we are running a lot of Kafka cluster for data ingestion to the Flink clusters, and then we have the Flink cluster as well. So why do we actually need the failover? The same case, so like one of the Kafka cluster goes down, we need to make sure that you can switch to a different Kafka cluster, and then still the entire data ingestion to those aggregations is still running, and then people are still able to get the real-time metrics. If one of the Flink cluster goes down, then whatever the jobs that were running in the old Yarn cluster, they still have to migrate to the newer one, so that there is a continuity of whatever aggregations that people are running. In case we are doing scheduled migrations of the Kafka clusters for ingestion, or the entire Yarn cluster from one cluster to another cluster, and those are scheduled one, even for that particular case, we need to make sure that we have the failover system. And in cases let's say one team was owning of one particular critical job, but the responsibilities for some cases are changing from one team to another. In that particular case, that job that was running on a Yarn cluster scheduled for another team has to be migrated to a different cluster, so that you can make sure that isolation and the authentication and authorization, all those things are still in the place, and each team is responsible for owning up their own resources. So even the job migration for us kind of happens very frequently, where we make sure you can do that entire process seamlessly. So we'll talk about in these two terms, that how do we go about making sure that ingestion pipeline to those Yarn clusters for aggregation, how does that happen? So we have a fronting stream where all these different products pushes data to. And this stream then pushes data directly from two Kafka clusters. One is active stream and one is failover stream. Now this stream, when we talked about, there are main stream, Kong stream, log stream. So this system is implemented and replicated for each of the stream. So from here, instead of Kafka replication, we publishes it to both the places. We have separate region which are out of the scope of this talk. But yes, the data goes to both of these stream, and then we have a custom written tool. We call it SIF. What SIF does is that it always checks up for the consumers, which are the Flink job consumers, which consumes to a certain topic, and they always keep on checking into that where exactly is that offset of those particular consumers, and it keeps on recording that particular data, and we record that data for the retention period of that particular Kafka cluster. So if the Kafka cluster has a retention period of 7 days, then we record that particular, for all the Flink jobs, we record those consumer offsets for 7 days. So that makes us sure that if we have the data, then we can run the aggregation from that endpoint. Doesn't matter even if the entire cluster goes down. So how the entire process looks like is that as soon as SIF keeps on monitoring these clusters, so as soon as SIF get to know that, okay, active stream is dead for some reason, let's say the entire cluster is out, then it makes sure that it switches all the consumers, the right offsets, and then it sets up these offsets to the failover stream. So all the consumer offsets of all the running jobs from the older clusters are seeked point to the failover stream. Now what can happen is that now we need to do two things. One is to, since Datlantis is managing all the jobs, all the people, all our users write entire jobs, everything on the Datlantis. So what we do is that we make sure that the new configuration of this new Kafka cluster has to be communicated to the Datlantis. So as soon as SIF get to know that, it communicates it to Datlantis, makes the API call, just tell it, okay, that Kafka cluster is down and this is the new Kafka cluster on which you need to run the job. And then as soon as that happens, the SIF moves the consumers and then restarts the jobs again with the new configurations. And since offsets are already managed, then the data, we never lose the data, and then aggregation starts from the same point. In very rare cases, we see a very small fluctuation of the data aggregation being ruined, but that's in most of our cases that's okay. Yeah, so this is how it happens. Now the second thing is that how we do the Flink failover. So in the similar case, like input stream is sending data to yarn clusters which are running the Flink. So there is active cluster and then there is failover cluster. And then similarly, Atlantis has information of all these clusters which it's running. So we have a service, custom written service Thor, in which we have different recipes. So in Thor, there is a recipe to migrate the entire jobs from one cluster to another, or it can even migrate a single job from one cluster to another cluster. So as soon one of the cluster goes down, then it notifies the Atlantis that I'm gone, and then all the jobs which were running on that particular clusters are migrated to the another one. So Thor notifies the Atlantis, okay, this is the new configuration of the new Flink clusters, and then you have to still all the offsets are already stored in the Kafka properly, so you can just actually kill all the jobs from the old clusters, and then with the new configuration restarts the job from there. And since we are restarting the job, it's not like for us, it's like everything is configuration. So all that configuration is stored in the Atlantis, the queries, the proper parameter. So we never have to ask user for any of those cases again. So we can actually on the fly, without even like involving user at all, we can restart all these jobs again. So this allows us to like make sure that even if our input stream to all this aggregation goes down, we can still make sure that everything is up and running. We can allocate jobs dynamically to different clusters. If one cluster is getting like heavy on the resources, we can spin up another cluster for the same team, and we can still distribute the jobs across. Testing and upgradation becomes really easy. If we are very not sure of if upgrading of version of Yarn or a Flink on one particular cluster might be risky, then we can even in the production spin up a new one, try some jobs there, and then migrate the whole jobs there. So we don't have to really worry about upgrading the same cluster and making sure of that. It becomes really easy and risk-free for us. The whole system becomes very self-serve, like user never have to care about in terms of availability, resiliency, or anything. So that all that is taken care in the behind. The another very important aspect is that how do we run the chaos and log testing. So whenever you launch a new cluster and then the team comes up with, okay, we will be running these many jobs on these particular clusters, then how we make sure that whatever resources, like how many worker nodes or these configuration we launch a new cluster with, it's good enough for that, for those things. So we have a custom written tool we called Loki, and then Loki takes care of disaster simulation, load testing. It generates the reports, and we give a CLI interface to our. This tool is not really for our users. This is more for the data engineers who are operating all the systems. So in this talk, I won't go into very detail of the Loki, but I have a bit.ly link where in the blog we have written in very detail like how does it work and how do we take care of the things. On overview, this is how the architecture of this looks like. So Loki manages certain resources. So it can even launch one Firehouse, which is a consumer on one particular Kafka cluster. It can launch feeder, which are like custom data ingestion. So it can generate custom data and launch on and run on a Kafka cluster. It can launch fronting, which is like OMS simulation of producing data from one OMS. And it can even play around with Kafka, like getting one broker down or everything. And then it can also do the same thing with the Yarn cluster as well, like bringing the entire Yarn cluster or bringing one particular job down and like doing all those chaos things. So in simulation, we have like there is a JSON configuration a developer has to write for running any of the simulation, where they can specify how many consumers they want to run, how much data ingestion they want to run, and how many brokers or Yarn cluster or broker nodes or worker nodes they have to bring it down. And then this goes to the simulation agent, which makes sure of parsing those reports and everything. And then at the end, it just generates report around like what was the blast radius of the jobs, how many jobs got lost, how much data got lost, and everything. So this is how the like one simple configuration looks like, where you just specify which cluster you want to run it on, what was the case, do you want to make the disk failure, instance recovery, and all those things, for how long you want that cluster to be down and everything. And then you specify in feeders, okay, how much data and consumers you want to launch, how many job consumers you want to launch, and those things. So specify all these configuration. So you simulate so in very crude manner, you just simulate how much throughput you want on the ingestion for the Flink jobs, and then you run some chaos in terms of bringing one system down. And then at the end, it generates reports. And then out of those reports, we come up with the patterns. Okay, if this particular thing is happening, then this is the remedy you need to do. Maybe if like 10 jobs got down, then you just need you need to spin up a new cluster or something like that. Very crude manner. So we just generate playbooks and we just write custom recipes around that. That if we know that okay, this was the case which has already happened in the chaos or the simulation, then you can just run that recipe even in the production environment, and then it's like we don't have to spend much time into those particular cases. We've already seen those failure cases. These are some of the reports generated where it shows the dashboard in terms of like ingestion, how it happened in the chaos, how produce time changed when chaos happened, lead accounts under replicated partitions, load CPU and disk usage and everything. So the Loki generates these particular reports. In terms of road ahead for us is that till now we have been running the entire Flink mostly on the Yarn clusters, but we have been experimenting on Kubernetes as well. So going forward, our plan will be to migrate like most of the things on the Kubernetes. We haven't like really played around with the complex event processing, but we have a lot of use cases where we can utilize those particular things. So that is one thing we will be like working towards, and then definitely like data enrichment with the Flink itself. Yeah, that's all from us. We'll be like open to questions. You can follow us like me and Sumanth and check out like blog of the engineering where we talk about like some of these components in more detail, that how that works and then the architecture looks like. But yeah, thank you so much, and now we are like open to questions. Thank you. Sure.
How do you handle schema evolution and replay data if needed?
Sure. I can answer half part the schema evaluation. So the way schema evaluation happens is that there is a central repository which hosts all the protobuf schemas. So if any team wants to make change, most of the teams own their own message types, right? So if let's say it's a booking log and then there is a transport team which owns that particular like schema, they will come and they will raise a pull request into any of the change they are making, and then they raise a pull request, review that pull request, and then when we upload the newer version to all our applications through the descriptor which Sumanth talked about, so that it get distributed to pretty much all the applications. Sumanth, you want to pick up the second part of the question? The replays.
To answer your question, the complete details would be this. So we use protobufs, and the proto compiler has an option called descriptor out. So when we give that option, it generates a file which is very small in size. And what our pipelines do is that they name the file with the version and basically just uploads it to a file server. Now, this file can be downloaded by any of our applications which have anything to do with these schemas. And at runtime, they're able to understand the descriptor and create or you can build a message or parse a message using that. And so when we say this, so all the applications, including the Flink jobs or even our custom Kafka consumers, they have this version number locked as a configuration. So if somebody has run a consumer and they want to rerun with a different version, they just have to change the configuration. And the tool which we had called SIF, which plays with consumer offsets, so you can point it to a point in Kafka ingestion time, and it'll reset the offset of the consumers to that point in time, and from there you're able to rerun with this new configuration which has a different schema. Does that answer your question?
And that's how even you can run the replays as well.
And if it's even older than the retention?
Then the only thing is that all the data goes to the cold storage, right, from warehouse. So then another option is then you pull data from there and then you can run the aggregation.
So this is a feature which we provide to our platform users, that any team publishing data into the Kafka will have all that data available in Google Cloud Storage. So we have some apps which are continuously running and pulling that data and storing it in cloud storage as Parquet format, which can be loaded by Spark jobs for any analysis later on. So, and based on the criticality of the topic, we have pretty good retention. Like one of our Kafka clusters has even a retention of 3 months, which is
so
pretty good for most
if you look at here, we talked about So here there are like 4 Kafka clusters, right? Stream, mirror, and then failover. So for each Kafka cluster, there are like 3 more Kafka clusters. So this mirror has a much higher retention. This is not where all the active consumers listen to, but this has a much higher retention. That, let's say, mainstream, we only need 7 days retention, but the mirror usually has, let's say, 3 months of retention. So you can even, if that 7 retention from the main cluster is not enough for you, then you can even listen from the mirror in that particular case as well. So similarly, like we have for failover and performance testing as well. So yeah, that's one case. And then even if that is not enough, then as Sumanth mentioned, we have like data stored in the cold storage.
All right. Unfortunately, we've run out of time. Please join me again in thanking Ravi and Sumanth for a fantastic talk.
Thanks, guys. Thanks for having me.
Thank you.